Hello, welcome to another cosmology talk. This week I have Adam Riess, who is a professor at Johns Hopkins University and an astronomer at the Space Telescope Science Institute. He was actually put in touch by a friend of the channel, Tommi Tenkinen, who's also at Johns Hopkins, before this paper has been released, which is actually a format I'm kind of keen to do more of. So if you have a paper coming out soon, get in touch. The paper is on crowding of Cepheids. In other words, is the background estimate of the background behind Cepheids doing the right job of calibrating their luminosities as part of the distance ladder. And obviously this is important because H naught is important, and we need to double cross every T and double dot every I to make sure that all of the normal physics that we're modeling is correct, because this could be fundamental physics, so we really need to be careful and check everything. That's obviously a very, very technical topic, and while he's here, I'll also ask him some general questions about H naught, so stay tuned to them. But anyway, thanks, Adam, for giving the talk. And do you want to maybe start by briefly summarizing what it is that you do in the paper?
Sure. As you described a little bit, there's this very exciting, very puzzling tension in the Hubble constant between local measurements and the early universe, and we'll get into that. But certainly one of the leading methods, and I think maybe the most precise, involves measuring distances using stars called Cepheid variables, which are pulsating stars. Perhaps the only, I might say, non-trivial bit of making those measurements involves evaluating the background of Cepheids, how much light sits inside the resolution element of a Cepheid. And we have been following what I would say is the conventional approach that everybody has for maybe 20 years, which is, to measure the background nearby and assume that it's the same as what's at the location of the Cepheid. But as you say, extraordinary claims require extraordinary evidence. We're seeing this tension, and so we really need to check everything. And so we came up with what I think is a kind of a cool new technique for directly evaluating what we call the crowding, or flux superimposed on the Cepheid, and that is by measuring another property of the Cepheid, the amplitude of its light curve, which would be directly impacted by the same crowding. And there's a very simple mathematical relationship that we derive that allows you to use the amplitude as a direct test. And so what we found is that the crowding determined locally matches what we find at the position of the Cepheid as determined by the amplitudes, and that in fact we can rule out that this is an issue causing the Hubble tension at more than 5 sigma.
Cool. I mean, that's good news for theorists and model builders, but bad news for anyone who needs closure. So if people reading the paper or watching this talk a couple of months from now are just trying to remember what they took away from it, what would you want those two things to be that is still in their mind a couple of months from now?
Right. I guess I would say, the first thing would be that with this direct test from the amplitudes, we can, fully put to rest any concerns people have about the accuracy of the Cepheid measurement itself. Certainly, the parts that were non-trivial about it. I guess the second thing, and I always need to remind people of this, is that it's not just this measurement or that measurement in tension. There are actually many corroborating measurements. That's why I think people have been so excited and so interested in this subject is, I can't give you a scenario where any one measurement, method, or technique that if you eliminate it, the tension goes away, because there's so many cross checks now. And so even though we want to do everything we can to understand the measurements that we've been making, and try to push them to get to 1% if we can, it's not that it all hangs on really any one measurement at this point.
Is that also true of the early universe? Like if you remove
Yes, it is. It is. As we get into, I'll show you a few slides that'll sort of remind you of that a little bit. I will.
Cool. Yeah. So the next question is why did you do this? I mean, we've covered this a little bit already, but if there's more detail you want to go into about that question.
Yeah, I mean, there's the due diligence part. I wouldn't, normally have woken up and said, oh my gosh, I need to check that the background region around the Cepheid matches at the location of the Cepheid. But again, if the bar is high for saying there's new physics in the universe that the early and late don't agree, and so you really have to go down this list and go, is there anything that could go wrong in this measurement? And so when we had this idea to do this, this seemed like something to do.
Yeah. And I guess specifically why, because there's maybe lots and lots of potential systematic errors you can check. Why was crowding the one that you chose to do now? Was it
Yeah,
easier to do, or was it more likely to be the cause?
I think it's, I would say it's, as I said, it's the only non-trivial bit, I would say, of measuring a Cepheid. It's a star. We observe its flux with the Hubble Space Telescope. We measure and turn that into a distance measurement. It's all, I would say, very straightforward. And maybe this was the one non-trivial bit. It's like any problem in backgrounds in science. Right now, we're all trying to figure out how many people are dying of coronavirus, right? And we don't know exactly, but if we measure, how many people die at normal times, we could subtract that and get the estimate of coronavirus. And so, that's basically, it's a background subtraction problem. It's important.
Cool. So now let's get into the deep dive into the details. What did you do in the paper? And maybe bring up the slides now if you
I'm going to do that now. So the title of the paper is "The Accuracy of the Hubble Constant Measurement Verified Through Cepheid Amplitudes." My sort of punchline might be Cepheids passed their final exam. It's final exam time here in the U.S. So lots of students are taking their final exams. Why shouldn't Cepheid variables? And of course, this is work I've done with colleagues Wenlong Wan at Johns Hopkins, Stefano Casertano at Space Telescope, Lucas Mockery at Texas A&M, and Dan Skolnick at Duke. These are people involved in the SHOES team, which is our team that's been measuring the Hubble constant for the last 10 years or so. So let me go on to, sometimes this catches, there we go. The Hubble constant, I don't know what you want to call it, tension, discrepancy, pandemic, crisis. I think, I've watched a few of your previous talks, so I know that you guys have covered this to some degree, but, simply put, the late universe measurements of the expansion rate of the universe, the Hubble constant, are significantly higher than the value you infer from early universe physics, from, describing the early plasma of the, pre-recombination universe that's used to determine quantities like the sound horizon or the baryon density. And then that combined with, cosmic microwave background observations or other tools, and in concert with vanilla lambda CDM, as we understand it, as we understand dark matter and dark energy, that predicts a Hubble constant, and those two disagree by about 5 sigma.
I think one thing that's worth stressing, I mean, cosmologists are totally aware of this, but if there's anyone from the general public stumbling across this is still a miraculous agreement. If you think about what the expansion rate was when the CMB was being formed, because it goes as a scale factor to the power of 9. Because it's the fact that it agrees that you're right. 67 on one side and 73 on the other.
We're only off by 9%, but we think our error bar now is below 2%.
Right, but we've extrapolated a number over an order of a billion. So I just wanted to.
But this is, this is the end-to-end test for cosmology. I mean, this is saying, can we start at the beginning, take our understanding of the physics of the universe, run it to the end, and actually match what we see? And the answer is almost, but apparently not quite. So just to proceed then, so the way we have been measuring the Hubble constant, the expansion rate of the universe, is by a very simple, what's called a distance ladder, where you take a tape measure and you measure the distance to these pulsating stars called Cepheid variables. Of course, not a real tape measure, but parallax and other techniques like that. And then you observe those Cepheid variables in the hosts of nearby Type 1a supernovae. So you calibrate those. Those are also standard candles, but much more luminous. So we see those all the way out into the Hubble flow. And so it's a very, I would say, simple, empirical, as long as you make the measurements right, this should be fine. And what I show there on the right is a recent conference summary of many different techniques now that have been used to measure the late time or current expansion rate of the universe. And then in the upper left there, I have a couple of representatives of the early universe. So we have Planck, so that's the cosmic microwave background, which all by itself, in concert with lambda CDM, gives you 67.4 plus or minus 0.5. But alternatively, instead of using the cosmic microwave background, you can use Big Bang nucleosynthesis. You can use estimates of deuterium abundance, primordial, that's measured by very unprocessed galaxies, and use that to calibrate essentially the sound horizon, which is what baryon acoustic oscillations need in order to then measure the expansion rate of the universe, into the present time. And so that route, no matter what you sort of do, gives you around 67 to 68. You could alternatively use other CMB experiments, WMAP, SPT pole. When you combine them with baryon acoustic oscillations, you usually get this number that's 67 to 68. Whereas in the late universe, while there's some variation, the sort of average is somewhere around 73 to 74, and depending on which combination you use, that's anywhere from 5 to 6 sigma. And so this is very concerning. And because we work with Cepheids, we're doing everything we can to test that. So going on to the next slide, why do we use Cepheid variables? And they've been used for coming on maybe 100 years, going back to Henrietta Leavitt Swan. And it's because, Cepheids are about the brightest star that we can recognize. And so therefore it gives us the longest range for measuring distances. So there's many type 1a supernovae that you can calibrate. They have the most opportunities to sort of geometrically calibrate. So I mentioned parallax, but there are other techniques, detached eclipsing binaries, megamasers in the host galaxy, NGC 4258. These are all independent geometric ways to calibrate it. We can measure them consistently. That is, we can use the same telescope, Hubble, to observe Cepheids in, let's say, the Milky Way, where we measure parallax, and then out in the hosts of type 1a supernovae. And they've been, I would say, the most vetted. And so here's a nice little diagram that I made recently showing this is the last 20 years of different people measuring Cepheids and type 1a supernovae to measure the Hubble constant. And you can see the results been very solid for the last 20 years, something like 72 to 76, and that's despite different people doing the analysis in different ways, using different sets of supernovae, different sets of Cepheids, making measurements with different instruments on HST at different wavelengths, different techniques for measuring photometry. And so, as we struggle to figure out what's going on, we thought more and more about, is there anything, that you could say still is a concern? And so that's what I wanted to talk about.
Can I ask
in this
a quick question that I feel is probably a slightly silly question, and I think I know the answer,
Sure.
but the reason why you obviously need Cepheids as part of this distance ladder is there just aren't enough supernovae to get enough local measurements, or if a supernova goes off locally.
Yeah, you're right. Yeah, that's basically it. Type 1a supernovae are so rare. There's only, one in a typical galaxy, every 100 years. So generally we cannot measure geometric distances out very far at all. And so there just aren't type 1a supernovae in the couple of places in the very nearby universe that we can measure geometrically the distance. And so we need some kind of go-between then. So the one challenge that I'll now describe, the one thing that I would say was is a little non-trivial, although, as I said, people have been doing this for 20 years. We didn't, invent this, is, this is an idealized picture of what it means to measure the brightness and distance for a Cepheid variable. So you see there in the center is a star, a Cepheid, but it lives in what we call resolution element. So that is to say, you can't really distinguish anything inside that inner circle. You're just trying to measure, all the flux that's in there, and maybe you're measuring it relative to the sky. But as I said, this is an idealized case. Here's reality, right? Reality is there are other stars in the field of view, other field stars, and sometimes those stars will land in the same resolution element as the Cepheid, and that's what we call crowding. Okay, and as you might imagine, right, how do you figure out how much crowding there is? Well, you can do this statistically, right? You basically sample the local background. You sample that annulus, really, that you see in the picture on the right. You might even throw down fake stars and measure them to reproduce the process, and you measure what's called the crowding, or really the offset or the bias that results on average from the other field stars that are crowding into the resolution element. Now, there could be extra wrinkles in this. It might not just be field stars. It actually could be stars that are physically associated with the Cepheid. That is, they live together. You could think of like a cluster that the Cepheid could live in, something like that. And so, this is something that, as I said, is maybe the only non-trivial part. I grabbed this quote recently from Wendy Friedman's paper that, possibly the most significant challenge for Cepheid measurements beyond 20 megaparsecs is crowding and blending from redder stars, particularly near-infrared observations. And that's because your resolution is even less in the near infrared for the Hubble Space Telescope, for instance. And so this was, as I said, I think it was something that was dealt with in the conventional way by sampling the backgrounds nearby and assuming what I think is reasonable, that, the Cepheids don't know that we're looking at them. And so what that means is, our line of sight to a Cepheid is random. And so it's just as random as, anywhere else nearby. And so this approach ought to work. However, we recognized a really powerful and direct, I would say, measure of the Cepheid crowding is to actually study the amplitude of its light curve. Okay, so here's now the same cartoon that I was showing you before, except instead of just showing you the Cepheid at one phase, imagine that the Cepheid is changing its brightness as it does. It's at minimum, it's at maximum, maybe it's at mean. Mean is what we usually use as the measure of distance. And you realize that whatever the contaminating or crowded stars that are in that resolution element, however much flux they have, that crowded flux represents a bigger contribution or contamination when the Cepheid is at its faintest than when it's at its brightest, right? It's a bigger fractional contribution when it's faint than when it's bright. And so what that means is, if you imagine the light curve, and so what you have on the right is the light curve, measured in astronomers' favorite units, which are magnitudes. And you can think of magnitudes as a fractional flux. Okay, and that's important, that it's a fractional flux. So for the uncrowded Cepheid that you see on the left there, you get the normal light curve, and it's kind of sinusoidal, and you measure its amplitude, and that's fine. But in the case where there's this crowded flux, it compresses the light curve because, of course, it's adding a constant amount of flux when the Cepheid is faint versus when the Cepheid is bright. And so as a fraction of the Cepheid, right, the variations now become smaller. And so you get this compressed amplitude. And there's a very simple mathematical relationship that we show in the paper, that the amplitude that you will observe divided by the true amplitude is 10 to the minus 0.4 times this crowding factor, this offset in the brightness due to the crowding. And so if you could measure the amplitude and compare it to what you expect it to be, instead of relying on the nearby region to tell you the crowding, you can actually get it directly from the Cepheid itself.
Cool.
So then there's one sort of calibration step, which we go through in the paper. Oh, sorry, before I say that, let me just show you 3 examples where this is, I think, makes this very clear. Here's a nearby galaxy that we use to measure calibrate a supernova. And here are 3 different Cepheids seen in that galaxy. You see this one up here is way out in the outskirts. So, you expect it has very little crowding because there aren't many stars out here. And, indeed, looking at its near infrared light curve, you see it has the full amplitude. It's a nice looking sine function. Okay, here's a case that's part way in. There's some stars around here, and this Cepheid has some crowding, and so you see its amplitude is flattened somewhat. And then here is one way in the heart of where lots and lots of stars are, and not surprisingly, right, its light curve looks quite flat. And the one below it is the optical or V band light curve, where there's very little crowding, simply because Hubble has much better resolution in the V band, so the resolution element is very small.
One question I had when reading the paper about this was, I guess, and this is completely naive question, I guess the assumption has to be made that the background itself is constant, that it's not also changing.
Yeah, well, variable stars and Cepheids are incredibly rare objects. So, a galaxy will have, 10 billion stars, which are constant, and then sprinkled on those are, a few thousand Cepheid variables. And so, so it's, maybe, once in a blue moon, so to speak, you could have, another variable in there. But, in almost every situation, it's going to be a constant background on top of a variable object. So then first you have to calibrate one little bit here, which is not all Cepheids have the same amplitude. Their amplitude itself depends on the period of the Cepheid. And so there we turn to the Milky Way to give us a sample of Cepheids that are both uncrowded, so we can know, what should the amplitude be in the absence of crowding, and then, what should the amplitude be as a function of period. And so we show, this is a key figure in the paper, but basically we show that if we form the ratio of the amplitude in the H band, that's the key thing we're trying to measure, to the amplitude in the V band, we actually normalize out a lot of the variation, and then we get a very simple quadratic relationship for this amplitude ratio as a function of period of the Cepheid. And so therefore we derive this simple calibrating relationship that tells us what amplitude to expect as a function of both the period of the Cepheid that we see and of the crowding that we see. And so then going on to, this is really this piece, this quadratic piece that just describes what the period amplitude relationship is. And so then finally, this is,
in the extragalactic stuff, we can't measure it without crowding, but we can measure the period very well.
Right.
So then we can predict
we can
what
measure
the
the period well.
signal should be.
Right. And then the Milky Way serves as the benchmark, right? The Milky Way, because, we could see Cepheids in the Milky Way without any crowding because, from our location, our resolution is, incredible.
Right.
And so we get, we get their uncrowded amplitudes. And so this is sort of the key figure in the plot. So what this is on the x-axis is the crowding that we measure locally. So that's the conventional approach. And on the y-axis here is, the ratio of the amplitude of the extragalactic Cepheid to the Milky Way. Okay. And, what we say in the paper, this is, maybe the key line from the abstract, that empirically measured amplitudes match the prediction. And so what you see here in black, this line is the expectation or the prediction of how the amplitudes will change with the crowding. And there are no free parameters in it. There's no choices here, right? This is exactly, how much compression of the amplitude for a given amount of crowding that you have to get. And you can see, that the data fits that very well. In red are actually binned versions of the data. And so what we see therefore is at very low stellar density, where there's no stars around, where the crowding is zero, then the amplitude ratio, the Milky Way compared to the extragalactic, is pretty much 1, because in the absence of crowding, extragalactic Cepheids, and this is a result from the paper, do have the same amplitudes as Milky Way Cepheids. And then at the other end, when the crowding gets very high, and in this paper, we go to regions that are much more crowded than what we would normally use to measure the Hubble constant, but we wanted to increase the sensitivity of this test. And so at those high crowding regions, then those amplitudes really flatten, but in accord with the prediction.
And this is the crowding as measured by putting like a fake star somewhere nearby.
Correct.
So it's
correct.
just testing that measure of crowding is kind of giving the right measure of crowding.
Right. That's right. So we measure the crowding as estimated locally and use that to predict what the amplitude should be. And indeed, the amplitudes agree with that very well. And so then we could take this one step further and say, okay, let's imagine that there is some, what I would call unrecognized crowding, some extra, what could be more or less flux in the resolution element of the Cepheid than the local region is suggesting. And so we then add a free parameter to the prediction of how much more or less flux there is, and require that to agree with the amplitude data. And so we form a chi-square statistic in the sort of standard way. And we find that the amount of unrecognized crowding that is constrained by this is about 0.029 plus or minus 0.037 magnitude. So, well within 1 sigma of being 0. But most interestingly is, we can rule out the hypothesis that there was, 0.2 of a magnitude. That's what a 9% difference in the Hubble constant is, about 0.2 of a magnitude, that we can rule out that possibility at more than 5 sigma. Or a very simple statement is that the amplitudes would need to be about 20% smaller than they appear to give evidence that there was extra flux that we were missing in the resolution element that would, explain the Hubble constant tension. So, I would say Cepheids, this is a null test, and Cepheids are passing this quite well.
Yeah, I guess it's one that you expected them to pass, but it's still
Yeah,
important
but
to
as
predict.
I said, I mean, something's got to give at some point, right? I mean, there's a
Yeah,
there's
yeah,
a
yeah.
difference. It's either cosmology or it's systematics, and this was, I would say, while I didn't expect it would be a systematic because we have so many other ways of looking at this, but nevertheless, it is the leading or only non-trivial part of the Cepheid measurement, and so I
Mm,
think it's
mm,
important from that standpoint. So, looking ahead, then what does this mean, or why is there this tension? And I'm a big fan of admitting my ignorance, and
mm,
this is one of those cases where I have to say I don't know. I mean,
mm.
it's so interesting because there are possibilities. I mean, I think the most attractive possibilities in terms of being consistent with all the data
Yeah.
is to change something in the construct of the universe at early times before recombination, basically. If you can think of a way that you can inject energy basically in the early universe, then you could cause it to expand faster. If you cause it to expand faster, then it becomes transparent earlier, and therefore the sound horizon, the distance that a fluctuation can travel up till that time, is smaller, and that
Mm,
changes essentially the calibration of the early universe. Now,
yeah.
that's easier said than done, because some of the specific ways that people have tried to do this, by adding a neutrino, by adding some early dark energy, they have to be just so to sort of not mess up the CMB.
Yeah, you
And
mean like
so
not produce spectral distortions that,
Correct,
yeah.
correct. And so there are papers that have demonstrated that they can do this, that they can solve the Hubble tension and even get a better fit to the CMB, but they are, what some people would say are fairly finely tuned,
Mm,
meaning, if there's extra dark energy, it has to be just in the decade of expansion just before recombination.
yeah,
And, as a observer, right, I get a little confused, I'll admit, by this discussion about what fine tuning even means. I mean, to me, this would be like the third episode of Dark Energy, and they all look finely tuned to me. I mean, why is the cosmological constant so small?
Well,
That's
I mean,
finely tuned.
but that, I mean, that's something that there's been in thousands of papers written trying to describe. So, I mean, that one's definitely a problem. But I guess
Right. But I would say, right. I mean, when you don't understand the physics and you describe it in a kind of naive empirical way, lots of things could look finely tuned. I hope,
no, but
one day.
that's
Yeah.
kind of the point, right? That you say when you describe it in a naive empirical way, it looks fine tuned, and so that's why theorists then want to find out why it isn't fine tuned. Like, what is
Right.
the physics
Right.
underlying it that
Of
makes
course,
it
of
completely
course,
normal?
right. So if somebody can understand that there's a reason, for example, that a scalar field of dark energy becomes significant just before recombination, and there are papers trying to do that. So if
Mm,
you do that in a natural way, then people say, oh, it's not finely tuned. Then in fact, it sort of had to be.
mm,
And so I think we're just at the point now where we are generalizing mechanisms that could, if you had a natural explanation, actually explain this. Another one, an idea I just saw just last week on the
mm,
archive, I cite the paper there, is if you had some kind of small scale inhomogeneities in the baryon
mm.
density before recombination. Now, that paper tried to do it with primordial magnetic fields. And, I learned in grad school, anytime you mention, magnetic fields, you sort of, jump the shark in terms of, you pulled out all the stops. But, maybe there's a natural way to have small scale inhomogeneities in the baryon density. I don't know.
Yeah,
But
and I mean none of the theories, as you said, sort of have come up to explain this have been super compelling. I mean,
right,
the late dark energy again is kind of, its amplitude is a bit tricky to describe from fundamental physics, but the idea of there just being a constant that has been there forever and is still there now is a step less in complexity than somehow you get something that wasn't there, or was there waiting to show up during recombination and then
and
goes
then goes
away.
away.
So I
Although,
think
what
we are
about
in a,
inflation?
I'll just finish
What
the
about
thought. Sorry. Oh yeah,
yeah,
inflation is
go ahead.
also a problem. But so we are in a state where there's no super compelling theory. So maybe people
Right.
starting to look at magnetic fields is not completely unmotivated. But yeah, okay, maybe finish your thought on inflation if you want.
Yeah. Well, I was just going to say, I mean, inflation is also finely tuned as well. I mean, it has to be just so, it has to disappear just so to not, mess up structure formation, to allow us to be here. And so I'm not I'm not telling you, one kind of dark energy looks natural and the other looks unnatural. I guess I'm saying, what I understand of natural, really, none of them are, if the definition of natural is, you put a bunch of physicists in the room, you don't show them any observations and you ask them to cook up likely physics, right? I don't think they would pick any of these episodes of dark energy without the observation, that the universe is incredibly flat, that, the universe is accelerating, and, maybe that there's a tension between the early and late universe expansion that, compels you perhaps to, or causes you to observe some, what you might just say is anomalous expansion that, has to be attributed to something.
Yeah, I guess my current boss here in Auckland, Richard Easter, has a nice way of describing this. I don't think it's original to him, but he uses it quite a lot. Is about visits from the tooth fairy, and
Right.
the late universe dark energy only requires one visit from the tooth fairy. It gives you the amplitude, but say in early dark energy, you need two visits from the tooth fairy. It needs to have the right amplitude, and it needs to go away at the right time.
Right. Well, what's inflation? How many visits would he say that is?
I think there are some models of inflation that only need the kind of one visit, because
Okay.
You don't need to fine tune when it happens. It could happen anywhere from electroweak symmetry breaking up to the gut scale or beyond.
Right. But what about the way that it has to disappear, the sort of E-folds, in order to, not continue to, spread material too finely?
No, well, I mean, yeah, most models of inflation, I mean, it comes a little bit of a chicken and egg thing. I mean, most models of inflation that people have looked at in great detail do kind of end somewhat naturally. It's normally getting inflation started that's the most tooth fairy-ish thing, that you have to have a sufficiently homogeneous universe for inflation to even start in the first place.
But I'm not telling you that it's early dark energy either is the solution to this. It is something that's been posited. Other things have been as well. I think, we really don't know at this point.
The suspicious thing about early dark energy would be that why is it happening at exactly the time where something interesting is happening to hydrogen? That's just so weird. That why would the early dark energy know what hydrogen is doing?
Well, I mean, maybe it has something to do with, radiation matter equality, or maybe it has something to do with an interaction between them. I think I've seen at least one or two papers arguing something like that. But anyway, as I said, I don't know, but, I think, this is how science works is, observers make measurements and they try to make them as robust as possible. And, theorists, help explain, what it is that we're seeing. In this case, I think, we're going to continue to try to improve the measurements. I think we've been focusing on a lot of things that could have been systematics that are, not showing up as a concern. This is just sort of my last slide to show is, the improvements I see just coming in the next couple of years. So the SHOES team is in the process of doubling the sample of calibrators of supernovae and Cepheids from 19 to 38. And, this will be the only doubling we will ever see because, there's only one that occurs about every year and a half or two. And so, it's taken us about 35 years for nature to produce this many supernovae nearby. We're not going to be able to do that again in the lifetime of Hubble. Gaia will have its data release 3 that should continue to improve the precision of the sort of geometric calibration of distance ladders. LIGO, we hope continues to find the kind of events that could give you standard siren measurements. DESI, LSST, W1st Euclid, these are all ways of characterizing H of Z, the sort of in-between period, so that, we can recognize either, look, it could be a weird late dark energy, or no, that's completely ruled out. Right now, I would say it's not looking good for weird late dark energy for, the equation of state being less than -1 as a solution, because, there is a lot of high redshift supernova and BAO data that says it looks like W is close to -1, but, we don't we don't have that part of the story nailed down as well as we would like. And then, the next generation of CMB experiments can look for signatures, particularly of things like early dark energy, which, have been posited as a possible solution. So I think there's a lot of activity on the observational side. There's a lot of activity on the theory side. This is definitely a progress report, but, we don't know the answer.
Yeah, so maybe I can ask you some questions. I don't know how much of a gambling person you are, but if you had to make a choice, like right now, of what you think the most probable explanation is on either the theory or observational side, what you think it would have to be?
Right. I think it's if I had to, I'd say certainly at this point, I would say that I'm fairly confident that something interesting is going on. And I don't consider, a systematic error in a measurement as interesting. So, I think something is not simple. And, I tend to look at the vanilla in vanilla lambda CDM, we take some pretty basic guesses about dark matter, cold, collisionless, stable, no interactions. We take simple guesses about dark energy. And in particular, we assume that at early times, the universe is pretty vanilla. And so, I have to say at this point, I'm starting to think something is not vanilla in this picture. And it might not even be any of the things we're thinking about, but nevertheless, I think something's not vanilla.
So you think it would be on the fundamental side, like it's not that there's some subtle thing about supernovae that we just don't understand correctly?
I don't think so. Yeah, because there are enough independent cross-checks. Right now, there was a paper a few months ago, just masers, geometric maser distance measurements out into the Hubble flow. You could look at this paper by Dom Pesce. I'm one of the collaborators, but there's no supernovae in it. There's no Cepheids. There's no tip of the red giant branch. We've seen, other techniques, the strong lensing, the time delays measured by the Holy Cow team. So they've measured 7 of these lens systems, and they're getting, the same thing that we're seeing, 73 to 74, plus or minus 1, 1.5. It has nothing to do with any of the other techniques. And so, I just can't think of a breakdown in any kind of tool that we're using that would explain all of these different things. So, that's why you have to start thinking about cosmology.
I guess there could have been a systematic error in the CMB that was subtle, but then, or the analysis of the CMB, but then as you pointed out, the sound horizon could be estimated from BBN.
Yeah, you could get the sound horizon from Big Bang nucleosynthesis. You can use WMAP or ACT or SPT in combination, or to calibrate baryon acoustic oscillations from that end of the early universe. And the only thing it uses in common with those other things is the the early universe physics, the sound horizon. Actually, one point I wanted to clarify. I know people often get confused about what is late universe versus what is early universe, and I have found a very handy rule of thumb to help you think about this, which is, if your measurement of the Hubble constant depends on how many neutrinos you assume are in the universe, then it's an early universe measurement. You're using early universe physics. You're really using the model of the universe at early times. And the universe is, if not dominated by neutrinos, they're a very important component of the early universe, which is why you need to know how many neutrinos there are when you do the calculation for the sound horizon. If you're doing a late universe measurement, you don't care at all how many neutrinos there are. It doesn't even make sense, the question, right? You're like, neutrinos, I'm measuring parallax, and then I'm using that to calibrate some different stars, or I'm measuring time delays. But, in the late universe, neutrinos have no role. So, and that's why we sometimes talk about neutrinos as, well, could there be another neutrino? Well, maybe so, that would affect things. But I like it most as a handy way to keep track of what came from the early universe and what came from the late universe. And I think it's quite amazing at this point how things sort themselves by this way. It suggests an answer, even though I don't know what it is.
Yeah, the fact that it just changing the early universe sound horizon kind of fixes everything is quite compelling to me. But then, of course, changing the early universe sound horizon without messing anything up is the difficult.
Yes, it's not trivial. The CMB data is very constraining, and so you can't just go in there, with a bat. You have to go in very carefully, and it's going to take just the right, the right physics.
So the one question I forgot to ask earlier was what your thoughts might be on some sort of breakdown, late universe breakdown of the FRW metric being responsible for this discrepancy
Right.
in H0.
Right.
Earlier, when dark energy was first discovered, people were trying to use this back reaction idea to explain the whole accelerated expansion, and I guess
right. It's certainly an interesting idea, and it's something you want to take a look at. But I think the problem with sort of any thinking along those lines is then you start to expect to see W of Z, the equation of state, not be -1, or for you to see really different values on different scales. So the expansion scale and the growth of structure scale. And so far, gosh, the H of Z information you get, which is independent of the Hubble constant. It's just, using high redshift supernovae or baryon acoustic oscillation, is really zeroing in on W being very close to -1, which, makes it very difficult to accommodate outside, sort of GR with lambda. Now, maybe, as we get to very recent times, we don't quite have enough leverage to see, that W is starting to take off and become much less than -1. And, that could be part of the story, but, it doesn't look like a smoking gun exactly.
Yeah, or whatever this deviation, it would have to somehow still look like W being -1 without it being exactly that. Cool, thanks for that. Anything else that you want to say that hasn't come up or anything?
No, I hope I hope anybody who's watching this or listening, I hope they're staying safe. And if you're watching this way after coronavirus has passed, I hope we made it. I hope we're still here. But if not, I hope the future picks up these questions, and you can rebuild civilization and still answer this one.
So the last question I normally ask everyone, and I'm really curious to hear your answer to this one, because it's most people say H0 when I ask them this question. But outside of your
Does
own
that mean
research,
I can't say H0? Okay.
No, well, because outside of your own research, what do you think is the most interesting thing in cosmology?
Oh, in cosmology.
Yeah.
I still consider LIGO in a way part of cosmology. I mean, I recognize that there's astrophysics, but in terms of what it could mean, finding things that you essentially could never see. And so I'm still very interested in this sort of zoo of things, the discovery opportunities of things that go bump in the night but without light. And so I'm very interested. I mean, they may lead to more tools for cosmology, but anything from understanding how did those black holes get so big? Could there have been primordial black holes, or is this the end state of stellar evolution and merging in clusters? So I'm very interested in that, and intrigued.
Yeah, definitely. I think whenever you look under a new rug, even if you think you know what's under the rug, it's amazing to hear what they're hearing, I guess. Cool. Well, thanks everyone for watching. If you like this video, don't forget to subscribe and click like and share the channel with colleagues. If you have any questions or suggestions, leave a comment as well. While you're here, you can watch another video. Last week's video by Kimmy Wu was on a very interesting aspect of the H0 problem, where they'd compared the SPT and Planck lensing, which were giving slightly different values, and really did a deep dive on the data and saw that it was related to the line of sight BAO. So they've done an amazing detective work there. What on earth it means and adds to the theoretical side is still to be decided, but it's a very interesting result. So thanks again, Adam, for the really interesting talk.
Thank you.